right, we're gonna look at the area between curves. So we've been doing area under the curve, right? And it's been between the curve and the x-axis, and we've dealt with, positive area, negative area, and just doing the integral of one function. So what's happening here is we have two functions, and we want the area between them. So we can do a little math here. So we have this one here, where we have I'll call it a top curve and a bottom curve. That'll be important later. We want to find that area between them, and we can do it with x values, right? We can find these intersection points to make our bounds. I'll just call this A to B, A to B. And then we'll do a little bit of discovery here in this right here, so I don't want to spoil it just yet. But we would use x values. And if we have something more vertical here, right, looks more like we have a right function and a left function, we do something a little bit different, and our bounds can still be from A to B, but we'll be using y values instead. All right, so let's get into this little discovery piece here. So, all right, that shaded area is what we want to find the area of, right? So we have one function is a parabola, and then we have another function that's that linear function. So how would we find that shaded area? Well, we know how to find the area under these curves. Let's see, I'll do this function in red, right? I could find this area, right? And then I could find, doing this color, I could find this area. And then notice that the green area is like an extra piece almost. It's almost like if I subtract them. So it's almost like I find the integral from a to b for f of x dx. And then I subtract off the area of the other one. And I'm just left with that green chunk. So I can combine these. And I can say, all right, big chunk is f of x, negative 1/2 x minus 2 squared plus 6. And then I want to subtract off the other function. So 4 minus 1/2 x, right? And then dx. And then I'm only looking at from where they intersect. So from here to here, which looks like from 0 to 5. And I definitely colored in some extra pieces here. Let's see, red could be this one, and then blue is this one. A bit more of an accurate drawing there. And then I can apply the integral rules, right? So I'd probably want to expand all that out. So let's see, x minus 2 squared is going to be x squared minus 4x plus 4. And I'll distribute that 1/2 to it. So I'd have negative 1/2 x squared plus 2x minus 2 and then plus 6, and I'll distribute this negative. So negative 4 and then plus 1/2 x. Combine some more like terms. I'll do it over here because I'm out of room. So I have negative 1/2 x squared. Combine my x's. 2.5 make 5/2x. And then negative 2 plus 6 is 4. 4 minus 4 is 0. And then I can evaluate that. So I'd have negative 1/2 and then x to the third over 3, and then 5/2 x squared over 2, and then I can evaluate that from 0 to 5. So I'll make that what? Negative 1/6, 5 cubed, plus 5/4 times 5 squared, minus, if I plug in 0, I'm going to get 0 for all of that. And let's see what this will give. So 5 cubed is 125, and then I need to multiply that by a negative 1/6. So I get negative, let's just round, and then 5 squared times 5/4 is 31.25. So I get about 10.42 as my area for that shaded, green shaded area there. All right. So I was kind of not wanting to spoil it at the beginning, but in this type of function, we do the top function minus the bottom function, which is what I did here. Top function minus the bottom. And then over here, when we have a more vertical situation, we do right function minus left function. Okay? We do it in terms of y. So let's do a horizontal approach here. So find the area of the region bounded by x equals 3 minus y squared and x equals y plus 1. So I could graph that. So I can see what that looks like. You know what? Let's go ahead and do that. All right, so here's visually what that looks like. So that area between those two curves is going to be a right minus left scenario. And then the bounds, at least on this graphing utility, we can click on them and we can go with the y values from -2 all the way to 1. But I'll show you how to do it without. So, this is a sideways parabola. And then that's a linear function. It looks something like that, which is what the graphing utility showed. To find the bounds, we want to find the intersection points. So if both of these are x, we can set them equal to each other and solve. So I'm going to move everything to the right. So I would add y squared, and then I would subtract 3. I forgot my y there. So y squared plus y minus 2. So I have a quadratic here in terms of y. So can I think of two numbers that multiply to -2 and add to 1? So +2, -1, which would mean I have -2 and +1, which is what Desmos showed, right, as the y values. So my integral goes from -2 to 1. And then I do right minus left. So the right function is that quadratic piece, so 3 minus y squared, and then that left is the linear piece, y plus 1. And we're in terms of y, so we'll do dy. And then we can combine some like terms after distributing. So 3 minus y squared minus y minus 1 dy. Oh my gosh. So I have negative y squared minus y and then plus 2. And then I can integrate that. So negative y cubed over 3 minus y squared over 2 plus 2y. And we'll evaluate it from -2 to 1. I'm going to go up here. So -1 cubed over 3 minus 1 squared over 2 plus 2 times 1. And then subtract off if I substitute a -2. So -2 cubed over 3 minus -2 squared over 2 plus 2 times -2. Let's see what we get. So negative 1/3 minus 1/2 plus 2. Do some side work here. So that'll be 8/3 minus 2. And then minus 4. So if I go a little further here, that's going to be 8/3 minus 6. Let's make that 18/3. So negative 10/3, but it's minus. So we'll add 10/3, and then let's make this all in a common denominator. Let's do 6. All right. So negative 5. Negative 5 plus 12 is 7. 7 plus 20 is 27. So 27 sixths. But I can reduce that. 9 halves, right? They both go by 3. So our area is 9 halves. Right, what if there's multiple points of intersection? So find the area of this. We have two functions. They're both in terms of x. So it's going to give us a top minus bottom scenario here. We can verify that in a graphing utility here. I'm going to go ahead and do that just so we can make sure. So we got 14x plus x squared minus 2x cubed, and then we have x squared minus 4x, right? So I have two different sections of area that I'm going to find, yeah. So let's go back here. Maybe let's do a little visual here. So we have a cubic that is going to look something like this. And then we have a quadratic that'll look something like this. I don't remember exactly how it was, something like that. So basically what we have is we have this area, and then we have this area as well. So we have two different integrals that we're going to add together, and in one scenario, g of x is on top. So we have one function like this, and the other one where it switches. Okay, so we'll just keep that in mind. And then I just need the intersection points. Yes, on my graphing utility, I could just click, click, click. But let's pretend we don't have a calculator. So to find the intersection points, we set the functions equal to each other. So 14x plus x squared minus 2x cubed equals x squared minus 4x. I like the leading term to be positive, so I'm going to add the 2x cubed over, which means I'm just going to take everything from the left and move it to the right. So I have 2x cubed, and then I would have, here, let's do this. Now subtract x squared and then subtract 14x. So the x squared is actually going to go away. So I'm left with negative 18x. Take a GCF, and I'm left with x squared minus 9. So my intersection points are 0 and plus and minus 3. So on my little picture here, I would have an intersection here at negative 3. My picture's not the best. This is supposed to be at, still x is 0. And then x is positive 3. So my first integral is going to go from negative 3 to 0. And then we're going to have g of x, so x squared minus 4x. And then I'm going to subtract off f of x. So subtracting the 14x, the x squared, and the negative 2x cubed. And then the other integral is going from 0 to 3, and it's if f of x is subtracting off g of x. Right? So I'll distribute that negative and combine any like terms. So the x squareds will cancel out. So I'm left with negative 18x plus 2x cubed dx. And then I'll distribute the negative here as well. The x squareds will go away, and then I have positive 18x minus 2x cubed. And then let's evaluate. So negative 18x squared divided by 2 plus 2x to the 4th over 4. And we'll evaluate that from negative 3 to 0. And then add in 18x squared divided by 2 minus 2x to the 4th over 4, evaluated from 0 to 3. So clean this up a little bit, right? That's going to be negative 9, and then x squared plus 1/2 x to the 4th, and negative 9 times negative 3 squared plus 1/2 times negative 3 to the 4th. And we'll add in this big old chunk here. So 9x squared minus 1/2 x to the 4th. Subtracting off. If I substitute in 0, alright, so if I do 0 here, it's going to be 0 minus, and then whatever this value is. 9 times negative 9 is negative 81. And then 3 to the 4th is 81, but times 1/2. So let's see, a negative 81 plus 81 over 2 is a negative 40.5. So minus a negative really is going to leave me with 40.5. And then let's go here. So 3, that's going to be 81. And then that also is going to be 81 over 2. So that's going to give me the 40.5 minus 0. And then I will add those together. So 40.5 and 40.5 is going to be 81. So they happen to be the same area. All right, what if we have 3 functions? So find the area bounded by the following functions. Y equals 12 minus x squared, y equals negative x, and y equals 4x for when y's positive. Okay, I'm going to do my best to draw. So I have a downward facing parabola. It's going to look something like this. Y equals negative x looks something like that. And then y equals 4x is going to look something like this. So the area bounded by all of them is going to be this chunk here. Okay. Let's get a good picture of that. So I have 12 minus x squared, negative x, and 4x. So see, I was pretty close. And there's my intersection points. Okay, so I'm going to be looking at 2 different integrals here. Let's go back on my picture. Now this is not the best here. Let's fix that. That looks a little better. Actually, let's just start over. I have my axis, and I'll do 3 different ones. So I have something like this. Something like that. And something like that. Let's do purple. All right. So I have 2 different areas. that I want to do, right? This first chunk can go from here to here using top function minus the bottom function. So that would be 12 minus x squared minus the bottom function, which was negative x. And then I can get the bounds. So it's where those two pieces are equal. So 12 minus x squared equals negative x. I like when the leading term is positive. So I'm going to add the x squared over and subtract the 12 and then factor. So I think I can find two numbers that multiply to 12 and add to negative 1. So I'd get negative 3 and positive 4, which would be right here, right? Negative 3, and this one would be positive 4. But then they also, they don't intersect at 0, 0, but that's the bound I'm going to use it for. So we're going to go from negative 3 to 0. And then that other chunk, right, I can add in the integral from 0 to this intersection point, which I'll find in a minute. And then we have top function again, which is the 12 minus x squared. This time our bottom function is that 4x. So I want to find when, I don't want to go there because I'm going to need that space. I want to find when 12 minus x squared is equal to 4x. So x squared plus 4x minus 12. And let's see, two numbers would be probably 6 and 2. Positive 6, negative 2. So they're going to intersect at negative 6, which would be this point down here, and positive 2, which is going to be right here. So from 0 to 2. And then we can evaluate this stuff. So I'll just do some side work here. 12 minus x squared, and this would really be plus x. So I'd have 12x minus x cubed over 3 plus x squared over 2, evaluated from negative 3 to 0. Actually, I'll just finish this one out. If I plug in 0 into all of these, I get 0. And now I want to subtract off if I substitute in negative 3. So 12 times negative 3 minus negative 3 cubed over 3 plus negative 3 squared over 2. So that would be what? Negative 36 plus 3 cubed is 27, divided by 3 is 9. And then that'll be 9 over 2. And let's see what that's going to give. I'm going to throw that in the calculator at this point. So negative 36 plus 9 over 2 gives me negative 22.5, but that's minus a negative, so really 22.5. And then we'll add in the other one, right? So that's going to give 12 minus x squared minus 4x. So that's going to give us 12x minus x cubed over 3 minus 4x squared over 2, evaluated from 0 to 2. So I'm going to have 12 times 2 minus, and I'm just going to go ahead and get these numbers. So 12 times 2 is 24. 2 cubed is 8, so that's 8 thirds, and really that's 2. So then minus 2 cubed. Subtracting off if I plug in 0, which is going to cancel out everything. So now I'll just get that number. So we get 24 minus 8 thirds minus 8. Gives me 13.3 repeating. So 22.5 plus 13 point. We'll just do 13.3 to get an area of 35.8. All right. And that is the last of it. So if you have any questions, let me know.